We contribute a real-time pipeline that uses a single-view RGBD input to simultaneously reconstruct a casual scene with surface albedo, detailed geometry, non-rigid motion, and environmental lighting. In this live demo, we show the real-time reconstructed results, including the geometry, the appearance rendered with the original lighting, and various relighting results. In addition to switching to new lightings to get the corresponding relighting results, we can also change the viewpoint to show the fused 3D model of the performer. Our method does not require any template or motion priors. Thus, we can handle various naturally interacting motions between human and objects. In this result, a performer is interacting with a backpack. Our system tracks large non-rigid motion, realistically produces closed albedo and geometry, and generates realistic relighting results simultaneously in real time. Our system can also handle large collisions. In this sequence, we capture both the inside and outside of a backpack while it is manipulated. The closing of the backpack generates complex surface collisions, which is resolved by our system and faithfully reconstructed in real time. Here, we show another sequence. Our system simultaneously fuses the appearance and geometry of the scene and handles object collision in real time. Note that in this case, we have culled the performer out of the working volume. Multiple objects with independent or interacting motions are reconstructed by our technique. In this clip, a bear is manipulated by a performer to walk and dance on a desk. The scene contains various objects such as a static desk, a non-rigidly animated bear, and an upper human body which appears in the middle of the sequence. Notice that the reconstructed surface albedo, motion, and geometry enable realistic relighting of the dynamic scene in real time. Our system can also handle fast motions. In this sequence, the performer rolls his arms in front of the camera. Benefiting from our novel shading-based joint optimization, our system tracks this fast-rolling motion with severe occlusions, again in real time. In this sequence, the actor performs a boxing motion. The consumer sensor generates color input with a degraded quality. Even with the blurred color input, our albedo fusion technique still recovers a reasonable surface appearance, which also helps to reconstruct the fast motion scene in real time. In this demo, our system produces an loop-closed appearance model and a geometry model. It also successfully tracks the non-rigid motions of the performer in real time. Here, we compare our algorithm with two state-of-the-art techniques for real-time reconstruction from a single-view RGBD input. Since the other two methods cannot reconstruct the appearance of the scene as we did, we applied volumetric blending to their results in order to perform texture comparison. Because the tangential motion has so few geometry and texture feature cues, Newcomb et al. And Inman et al. Cannot track the motion correctly. In this case, an umbrella is rotated around its central axis. Note that in the two examples to the right, the input color gets blurred due to the fast rotation. It is difficult to detect geometry or SIF feature correspondences. Therefore, both of their methods fail in tracking this motion. In contrast, our method utilizes dense shading cues, thus successfully tracking this challenging motion. In this sequence, cloth is stretched by a performer. Again, the other two methods fail in tracking the stretching motion, thus generating severely blurred textures. Our system also outperforms the other two methods in handling collisions. In this sequence where complex surface collisions happen, both Newcomb et al. And Inman et al. Cannot update TSDF correctly, and thus fail to reconstruct the dynamic scene. Our technique is more applicable in handling casual and fast motion as shading information is exploited. In this comparison, we reconstruct a much better appearance, motion, and geometry. Notice the artifacts that appear in the other two texture results, which occur due to the misalignment between the reconstructed geometry and the color input. In the following, we show more comparisons between the three methods. Again, our method achieves a more complete reconstruction than the other two methods, because it recovers both the albedo and low-frequency lighting of the scene, in addition to the geometry. Our technique also enables many applications. First, we can produce high-quality relighting results in real time, as our system can faithfully reconstruct appearance, geometry, and scene motion. This cannot be achieved by either Newcomb et al. Or Inman et al. In this demo, we show relighting results of the same scene in various lighting environments. After tracking the entire sequence, we use the Final Fuse model for free viewpoint video synthesis using our proposed back reconstruction technique. Here, we render free viewpoint videos from the viewpoint of 3 virtual cameras. Without our albedo fusion technique, it is impossible to enable such an application using a single RGBD camera. The reconstructed albedo can also be edited to achieve realistic video editing, since our system reconstructs temporally and spatially coherent appearance and geometry of a dynamic scene. Our system also enables convenient 3D self-portraits in real time. During the scanning, we can easily create a complete and hole-free model in which the actor can freely perform natural and non-rigid motions. Here, we show a simple scanning process, in which we see the final upper body model with accurate geometry and plausible surface albedo. Thank you for watching. For technique evaluations and more comparisons, please refer to our secondary accompanying video.